So in this part of lecture, we'll show you the proof that the first order condition of the convexity is both a necessary and sufficient condition. So let's assume, so first we'll consider a scalar case where f is a mapping from a scalar to a scalar. So f is a mapping from a real space to a real space. Now assume that the points x comma y, both x and y, belong to the domain of the function. So as we know, the domain of function is convex if its domain is convex, and assume that this f is convex. So the domain of the function is also a convex set. So any point, let's assume that there is t which belongs to the set. So it is open over here and closed over here. So that what it means is that t is greater than 0 and t is less than or equal to 1. So for any point, so for any t, the domain of the function would satisfy that x plus t times y minus x also belongs to the domain of the function, which is nothing but the definition of a convex set. Since the function f is convex, so is its domain, and this is a definition of the convexity of a set, which we have shown in the previous part. So now, since the function is convex, we can write that f of x plus t times y minus x is less than or equal to 1 minus t times f of x, just use the definition of the convexity of the function, plus t times f of y. So this is the very definition of the of a convex function, that satisfies this inequality. And here we have assumed that t is greater than 0. So now we can divide both sides by t, since t is greater than 0. So we can write this as f of x plus t times y minus x over t is less than or equal to 1 minus t over t times f of x plus f of y. So now we can rewrite this as f of y is greater than or equal to f of x plus f of x plus t times y minus x minus f of x over t. So we just we just open this bracket, so we'll get f of x over t minus f of x. So this is our f of x, and we brought it to the left hand side. So we just have rewritten this inequality as f of y is greater than or equal to f of x plus t times y minus x minus fx over t. So now since x and y, we just assume that y and x are distinct points, so y minus x is not equal to 0, and also we assume that t is greater than 0. So now we can multiply and divide this by y minus x. So we can rewrite this as f of y is greater than or equal to f of x plus f of x plus t times y minus x minus f of x over t times y minus x times y minus x. So now if you remember the calculus, this is nothing but the derivative of a function at point x. So as we take limit t tends to infinity, so limit t tends to limit t tends to 0, this is the derivative of the function at point x. So for sufficiently small t, we can write it as f of y is greater than or equal to f of x plus f dash x times y minus x. This is valid for all x and y belong to the domain of the function f. So what we assumed is that f is convex. That was the only assumption, right? And we just use the definition of the convexity of a function, right? We just use the definition of convexity, and then we derived that if the function f is convex, then it satisfies this inequality for all x and y belonging to the domain of the function. So this shows that this is a necessary condition for the convexity of any function f. And now we are going to prove that this is also a sufficient condition for the convexity of function f. That is, if you prove that f satisfies this, then it is convex.